Good morning. I'm Jerry Alpern, a tour guide in the American Museum of Natural History, and we're in the Rose Center on West 81st Street on Manhattan's Upper West Side, and we're looking at the sphere of the Hayden Planetarium, uh, which is a complete sphere, 87 feet in diameter. And first of all, I am very happy that you are here with us on this journey, because this journey, as every good journey should be, is also a quest to understand the scale, the range of scales of the universe, from the entire universe itself down to the subatomic level. And in order to do this, we're going to require your cooperation, because you're going to have to use, I'm afraid, your imagination here. Here we're looking at the scale measures, because we're going to go from the Hayden Planetarium, representing the entire observable universe, which is 13.8 billion light years in diameter, although it's even more than that currently, as we'll get to, down through the galactic scale, millions of light years, stellar scale, a few light years down to the planets, and so forth, our human scale down to the atomic scale. Now, first of all, to get an idea of how we're measuring things, what's a light year? It's the distance that light travels in 1 year. Now, light, of course, is at a constant of 9.5 trillion kilometers is a light year, because the speed of light is about 300 300,000 kilometers per second. So, and please feel free and do ask questions, and especially if I make any howlers or bloopers, okay? Because we depend on you to keep us all honest. So, on the scale, when I say it's even bigger than 13.8 billion light years, it's because the universe itself has been expanding since it originated in the Big Bang, because the Big Bang was space expanded, not up at the distance between the stars, but the space that they're embedded in. So we're looking back 13.8 billion years in time to as far as we can. But since space itself has been expanding since then, it's now 46 billion years in the radius and 93 billion light years in diameter. So on this scale of if you assume that the Hayden Planetarium is the entire observable universe, then we're going to come here to our first object, which is the Virgo supercluster. This is, I have a question. Do you know what things were like before the Big Bang? No, we do not, because space and time originated at the Big Bang. So we have no direct way of knowing. There are a whole variety of proposed explanations, including multiverses, meaning we're not the only universe out there, but we do not know. The Virgo supercluster is made up of thousands and thousands of galaxies, each containing hundreds of millions of stars. So you've got, and yet this is only about 1% of the known universe. Now, So you can see the tremendous gap here between that. Now, how do we express this? You see a little 10 to the 24th there. Actually, we started at 10 to the 26th. That represents the number of zeros after a 1. And it's powers of 10, and it's the way to deal with the size of things rather than saying billion billion or trillion trillion. And incidentally, in the UK and the US, these words have different meanings, so you have to have scientific notation, and it's simply a power of 10. We start with 10 to the 26, and when we get down to the Virgo supercluster, we're already down to 10 to the 24th. But let's go a little bit beyond that now. And, excuse me, we're going to skip over. So, oh, wait, we should stop right here because this is our local galactic cluster in which we are. Oh, and you know what we're looking at now? Our very own galaxy, the Milky Way, which is, but on this scale, you have to imagine the Hayden Sphere is no longer the entire universe. The Hayden Sphere is now the size of that Virgo supercluster that we just investigated. So now we're looking at our local galactic cluster, but even there, the whole Milky Way is reduced to the size of a fly in some sort of cosmic amber. So let's go a little bit further on down, and let's see if we make the Hayden Sphere the size of our galaxy, of our local cluster. Now what do we have? We have the relative size of the Milky Way that we live in. So you see how fast we are now going down as we progress downwards. So you have to, again, imagine the sphere is actually an entire cluster of galaxies. But we want to get further down. Let's get down to where where the Hayden Sphere is going to be 1 light year in radius. Okay? That means that it takes light. Did we go past it, or are we coming to? Let's go to our left a little bit. Oh no, sorry. Haven't been in the museum for a while, so my memory's pretty bad. Here you have the not just the whole solar system marked by those rings, but the whole Oort cloud of comets that revolves around the solar system. The outer ring there is the orbit of Neptune. And the sphere is a single light year. Now, we're getting down, but we've come down several orders of magnitude. Oh, it's called the Milky Way. Well, it was originally called the Milky Way by the ancients because of a legend about Hera, the wife of Zeus, who was nursing his son Hercules, whom she didn't like. So because he had a different mother, so she pushed him away from the breast, and the milk spilled out, making the Milky Way. Now it's just because it does look kind of milky if you're on a good clear night somewhere with an unobstructed view. So let's go on from there. And let's go down and see if we make the Hayden sphere, the size of the sun. And now, what is the relative size of the Earth and the other planets? And here we have, look at this, we're down already to 10 to the seventh. Okay, so yes, stay in there on the rocky planets for just for a moment. These are the inner planets: Mercury, Venus, Earth, and Mars. Now, on this scale, 1,000,000 Earths could fit inside the sun. But fortunately, we're not doing this on a size scale, so we're not burned up by the light and radiation from the sun. If this were a distance scale, we'd have to have the Earth in Times Square, which is about 1.7 miles from where we are. So now, when we look at that, and you can also see the sizes of the gas giants, like Jupiter and Saturn here. So on the scale, that's all that Earth is. But we're going to go down even further than that, because this is a long journey we're taking. You really have to sort of hold on. Will the technology be advanced enough to go out of our galaxy and go into a different one? Oh, that's something science fiction writers have wanted for a very long time. But consider this: the oldest radio signals, when the dawn of radio began a little over a century ago, they've only reached, traveling at the speed of light, about 80 billion light years from Earth. So if you you have a choice of either traveling at the speed of light and figuring out some way to perpetuate your society during that time, or develop a warp speed. But we're not in Star Trek, so we can't really do that. But now, how many light years does it take to get to the? Actually, it takes 8 light minutes to get to the sun. That's how long the delay between the light coming out of the sun and it reaching us here on Earth. But let's go back a little bit, because I'd like to really drop down in scale now. We're going to go to the Earth being the size of a red blood cell. And yes, that's where we are. Look at what we've got now. Now, a red blood cell is very small. If you've got a drop of blood, for example, you have about 10 million red blood cells in that drop. And on that scale, what you're looking at, if this Hayden sphere is the size of a red blood cell, you're now looking at a virus. And we're picking this out in particular for the obvious reason of why I'm doing this by video. You're at home. We're all at home most of the time because of a virus. And the red blood cell is the Hayden sphere. This is where we're going down, and we're now noticing we're now at 10 to the minus 8th meters. This is a huge trip we've taken so far. What that means is you've now got the zeros are, instead of in front of the ones, we've moved the decimal place to the left, and we're now at I'm not even sure what I would call this, 1/1000th of a meter, I guess. But it's much easier to say, and you can be more certain of being accurate, to say 10 to the minus eighth power. And that's what we're looking at here. Um, with But when you've got a virus, it's, genetic material and proteins, various stuff. But what happens if we try to go below that level? If we go down, what do we have here? We are now at 10 to the minus 10th, okay? Now, imagine the Hayden sphere is now the size of that virus we just saw, okay? That's the Hayden sphere. So, what is it that we're looking at? We're looking at a single atom of hydrogen, except that what we're really looking at is a representation of the cloud of electrons that is in what we call orbitals around the nucleus, which is a single proton. We call it orbitals because if we said orbits, you'd think that it was like the planets orbiting around the sun. But it's really a set of probabilities of where an electron is at any particular time. So we represent it by that cloudy plastic sphere. But now imagine that the Hayden sphere is the size of that whole electron cloud of the hydrogen atom, which is, of course, merely a single proton. So now we are getting down even lower. What are electrons? Electrons are tiny charged particles, which are one of the subatomic particles that we have when you try to break an atom down. The proton at the center, do you see that little dot? That's really a small dot. I think it's like 1/180th of an inch, but I might be wrong. But look up. The Hayden sphere is the size of that whole electron cloud. Are quarks? Yes, quarks are smaller than electrons, but it gets pretty hard to show a quark. But think of the difference between the size of that proton and the size of the electrons inside the hydrogen atom. The hydrogen atom is mostly empty space, which means that you and I, are on that level, mostly empty space. There's just nothing there. But now you are interested in quarks. Well, go back to the labels there, and you'll see it takes it into account because it's a very interesting thing. If the Hayden sphere were the size of just that proton, or then a quark or an electron, it might be smaller than your thumbnail, maybe smaller. It becomes very difficult to put into physical shape, into like a piece of sculpture, the size of something that tiny in size. Because what you've got now is the universe. We've gone through this on sizes of 10. And what you started out with is 10 to the 26th. Okay? That's 10. We're down now. Look at that. 10 to the minus 18th meters. And even below that, we can't go. That's where this ends, 10 to the minus 18th. So you're talking about a scale of 10 that is powers of 10 that are little more than 40. Okay, about 44. The largest thing. Well, that sort of depends. What do you call a thing? Uh, the largest thing within the universe, you could say it's a supercluster of galaxies. There are various sort of definitions for it in the large scale structure of space, which is a fascinating thing. Space has developed over time, and depending on how you define it, you can have uh, assemblages of galaxies that are can be can be tens of millions, many tens of millions, hundreds of millions of light years across, depending on how you measure them and how you consider them. Because what's holding them together is a kind of gravitational attraction. And now we come to just something we'll touch on briefly is we're not sure what's out there. Einstein is supposed to have said that he only knows two things that are infinite: the universe and man's stupidity. And he's not too sure about the universe. It's how are electrons and protons alike? Well, electrons have got a negative electron charge, and protons, and again, correct me wrong on this because I am not an astrophysicist. I am a humble tour guide. Protons have a positive electric charge. Um, Again, please, somebody hop in. So the universe on both large and small scales is, yeah, isn't that really a surprise? It's That's what's out there, is a kind of nothingness. But what I was getting back to is that we don't really know what is out there, because I have a friend who also grew up near the museum, as I did, literally around the corner. And I once asked, he grew up to be a physicist. And I asked him, if you were here, what would you stress? And he said, the enormity of space and the incredible span of time. He says, and finally, ignorance. Because according to our current theories, we there the amount of visible matter in the universe and the amount of dark energy, and the amount of energy that we can measure is only about 5% of the universe. That there is dark matter out there making up maybe 90% of the universe, dark energy out there. But what are they? We don't know. The, these these terms are sort of placeholders, like you're throwing a dinner party in your house, a small dinner party, friends, family. But you also know that there are going to be two other guests coming, and you want to be hospitable. You want to put out a name card, a place card on the table, but you don't know who they are. You don't even know what they are. So you call one dark matter and you call the other dark energy. But you have no idea who will show up at the dinner table. And that, in fact, we're not even sure that they are necessarily matter, because just recently, a theory has been explored by scientists. There was just a paper on it a couple of weeks ago, that our understanding of gravity is not complete enough to really make a statement. The hypothesis was that gravity of any particular object is actually influenced and measurably influenced by the uh, matter of all the other objects in the universe. And this would be a little different than the standard model, as they say, which is the Big Bang and the expansion since then. But if we go back to looking at the Hayden Sphere and what's out there, what is the difference between dark energy and dark matter? What do we know about this dark unknown universe? Okay, the dark matter hypothesis arose through calculations that the matter that we can see in the universe does not account for our measurements. Something has to be there, exerting rather, a gravitational force far beyond all of the observed stars and planets and things that we can see. And that is what we call dark matter, because we know it has to be there because of its gravitational influence. Now, dark energy is slightly different. This arose somewhat more recently when the acceleration of the universe, the expansion of the universe, the acceleration has begun to increase, and we became capable of measuring it. Now, remember, we only learned about 100 years ago, Fred Hubble measuring the redshift of stars, that the universe was expanding. Einstein didn't know that because the discovery had not yet been made. So now we're finding that the expansion, and remember, it's the expansion of space itself. It's not that the stars are accelerating one from each other, although they appear to, but that the whole fabric of space is accelerating. And we don't know what's causing this acceleration, that things are speeding up. And this has a lot of implications. Are we going to go on and on until finally the universe just sort of peters out in a dark, lifeless void? Or are we going to start reversing course and ending up at what's been called the big crunch? Well, if our measurements are correct, this mysterious dark energy may eliminate the possibility of a dark crunch. Again, this is one of the hot topics in astrophysics because it is disturbing to know that all of these objects that we have are not everything that's out there. The energy that we can measure is not all the energy that's there in the entire universe. But our journey has been to try to understand this. As part of right near the scales of the universe here at the Rose Center, there's the cosmic pathway, which is a spiraling pathway starting at the Big Bang and ending in us. And it covers 13.8 billion years. And the fun thing about it is that all of recorded human history on this lengthy pathway, which winds down where you can cover close to 100 million years at every step you take, it's a single thickness of human hair. And that represents about all of recorded history, 30,000 years. And one last thing before we have to go. Of that 30,000 years, only about the last 10,000 years or so, we've had a stable atmosphere where we have been happily doing our civilization, meaning trade, meaning meaning settled big cities and things. And right now, we're changing the conditions under which we live by the changing climate faster than at any time we can measure in the past history of humans. So think about that. Anyway, thank you very much for sticking with me. The museum is open. It is open Wednesday through Sunday by timed admission. And we hope that you will come here in person to see the Rose Center and all of our other wonderful exhibits. We miss you very much. Thank you.